Oh, thank you very much for having me. I'm very excited to present here, and thank you for inviting me, Youngsu and Tony. Um, as Thanks for also for the introduction. As Tony mentioned before, as of a couple of months ago, I'm at Stanford. But before that, I was working on my PhD and on my postdoc at ETH Zurich. And in this talk, I wanted to bring you an overview of that work that came out of that time. And this, in general, concerns model reduction applied to fluid dynamics, mostly, and from the point of view of invariant manifolds. And so that means it's mostly going to be joint work with George Haller, in fact, all of it, and also with other collaborators who will be acknowledged as I go along. So I'm going to discuss fluid flows. So that means I'm going to look at solutions of the Navier-Stokes equations, which I have here. And as a bit of foreshadowing, here I have two systems that will be mentioned. On the left, it's a turbulent pipe flow, and here this is a fluid structure interaction problem. And some dynamical systems insight turns out to be quite helpful for these kinds of systems. It was proposed a while back that we should look at solutions of this equation as evolving in an infinite dimensional phase space. So this would be the function space of velocity fields. And that means a fully time resolved solution or simulation or experiment would be really nothing else, just a trajectory of this dynamical system that I written sort of in a symbolic way as u dot equals n of u. And of course, in practical applications, this is never actually infinite dimensional, but very high dimensional because of the spatial discretization that we always have to do. So it could be 100,000 or million degrees of freedom. And this phase space is actually filled with special solutions. In the dynamical systems language, these would be fixed points, periodic orbits, quasi-periodic orbits, and so on. And in this line of literature, they are called exact coherent states or exact coherent solutions, ECSs for short. And it's even though a trajectory could be very complicated, it would be sort of described by the motion between these, the pinballing motion between these exact coherent states. And so this will be very important for later. And as an overview, I'm going to discuss, to be a bit more specific, I'm going to discuss dynamical systems in this form. So x dot equals ax plus some nonlinearities, where x comes from a finite dimensional, but possibly very high dimensional vector space. And if there's one point I want to make today is that one of the most important difficulties that comes with a reduced description of these types of systems is the fundamentally nonlinear or non-linearizable behavior that can arise. And one hallmark of that would be when I know that there are multiple steady states that coexist in the phase space. So they are competing with each other. We have multi-stability. Or we have this very complex, chaotic, or turbulent behavior. If these are true, then I know that I have to somehow turn to nonlinear methods for reduced order modeling. And I could do that from 2 points of view. I could use the equations, or I could use data directly. But using the equations is quite difficult usually, just by the nature. It could be by their nature, they are very high dimensional. They might be PDEs. But more importantly, I might not even know them in practical applications, or I might not trust them enough. And so therefore, we usually turn to data-driven reduced order models. And if I want to do this reduced order modeling in a mathematically justified and defendable way, then one such setting where I know that is for sure doable is when I know that there is a low-dimensional attracting invariant manifold in the phase space of this dynamical system. So if you look at this sketch, you can imagine that there's this blue trajectory sort of coming down, attracted to this flying carpet, this green surface, and it synchronizes with its internal dynamics. So therefore, if I restrict my attention or restrict the dynamics to this invariant manifold M, then that would give me still a good overall description of the system. So this would be a good model. And this model is going to be simple because the manifold is low dimensional. It's also attracting. I assume it's attracting. And that's very good because I have a chance of actually observing this in simulations or experiments. It is also manifold, so that means the model is going to be smooth. And that is very good if I want to do calculus on it, for example. But even more important is that it's also going to be smooth in the properties of the system. So I know that it's going to be robust against perturbations of the system. And so that is very important for a model because I ultimately want to learn new things, things I didn't know about the system based on the model. And therefore, because of the smoothness, I can sort of extrapolate knowledge that I already have. And finally, what invariance buys us is that this is going to be a closed model. So as long as I'm on the manifold, I know that I'm for sure not going to leave it. So there is no risk of me running out of the domain of validity of this model. And one caveat that comes with this is that for this to be a robust construction, structurally stable construction, the manifold also needs to be normally hyperbolic. What this means is that the normal rates of attraction must dominate the tangential rates of attraction that happen inside the manifold. So that means the dynamics outside the manifold must be much faster than inside the manifold. So people call these slow manifolds usually. And what happens if this is not the case? Well, here's an example of an attracting manifold, invariant manifold, this red one that is not normally hyperbolic. You can see that the normal rates are much weaker than the tangential rates. And so what that causes is that a general trajectory, it's not even acknowledging the existence of the manifold. It's just sort of flying by, and it's only attracted to it right at the very end when it's converging to this fixed point. So I would say that this is not a very good model of this system, probably. But if we look at a normal hyperbolic invariant manifold, like this green one here, you see that the normal rates actually dominate the tangential rates. So what that results in is that trajectories are compressed and they are pushed together towards this manifold, and then they converge synchronized with the internal dynamics of the manifold towards the fixed point. So this would be a very good model. And now, if the existence and uniqueness properties of these manifolds are cleared up, and that's a big if, by the way, but if they are, then I can now attempt to parameterize them to construct them. And then what I would do is pick a smaller set of reduced coordinates, such that I can model their time evolution separately with something called the reduced dynamics. In most cases, in our applications, these will be low-dimensional ordinary differential equations. And I know that as long as I'm on the manifold, the dynamics is consistent with what's happening in the phase space. So that means on this manifold, I can always return to the full phase space with this so-called parametrization map. So I'm not losing any information. And one more thing to point out is that this is a very popular idea nowadays, especially with machine learning methods and artificial intelligence-based methods. People talk about the manifold hypothesis, so that data generally tends to live on lower dimensional subsets of the ambient space. And in fluid dynamics, especially, this goes back to the 80s with discussions on the inertial manifold, which is an invariant manifold that contains all of the global attractors of the system. And unfortunately, in full generality, it hasn't been proved for the Navier-Stokes equations that they would exist, but it's still a very nice sort of line of thought to keep in mind. And what I want to introduce now is a special class of invariant manifolds that, as you will see, they automatically put us in this very nice slow manifold or normally invariant, normally hyperbolic invariant manifold setting. And I just want to introduce or motivate that very shortly. So imagine this system that I've written down before, but now let's neglect the nonlinearity. So imagine that this is a linear system, x dot equals ax, and I have a fixed point in the middle somewhere. I'm assuming that this is hyperbolic, but this could be stable or of saddle type, so it can have both stable and unstable directions. That doesn't matter. But in this case, I know that reduced order modeling is very easy, in fact, because eigenspaces of this linear operator are all invariant. And by superposition, even their collections, which we call spectral subspaces, are also invariant. So therefore, if I want to reduce description, I could just project onto the slowest one of these spectral subspaces, and that would give me a very good model that is exact in some sense. And everything else is just attracted to this low spectral subspace. And the good news is that under fairly generic assumptions on the linear part of this dynamics, this can be shown that this picture is essentially the same in the nonlinear system, so that there is a similar slow to fast hierarchy of invariant objects, which now they are invariant manifolds, and they are tangent to the underlying spectral subspaces of the linearized system. They're also anchored, just like the spectral subspaces are, they're anchored to the steady state that I assumed is there. In general, this would be a generic exact coherent state. And not only are they tangent to the spectral subspaces, but they can be viewed as nonlinear continuations of these spectral subspaces, or nonlinear extensions of the spectral subspaces. But now they can carry nonlinear dynamics, so they can support multiple fixed points, limit cycles, and even more complicated attractors, as we will see later. And again, the most important one is the slowest one of these spectral submanifolds, the slow SSM. Yeah, we call them spectral submanifolds because they grow out of the spectral subspaces, SSMs for short. And we're usually going to concentrate on the slowest one of them because that acts as an attractor. Because everything else outside this SSM is pushed towards this SSM, and this gives me a good reduced order model. So to start with, I want to show you an equation-driven example. And this is very simple. This is something you can do with pen and paper. I took this example from the book of Guggenheimer and Holmes. I modified it slightly, but I think this will be helpful to go through once. So here we have x and y coordinates and a fixed point at the middle, so at 0. And also, this is already in diagonal form for the linear part, so I can immediately read off the slow spectral subspace, which is the x-axis. That is an invariant subspace for the linearization. And by what I told you earlier, it follows that then there is an SSM, a slow SSM, that is tangent to the x-axis. So then if I want to find it, then I could assume that that this functional relationship holds. So the other coordinate, the y coordinate, is subordinate to the x coordinate with this h function. And I could now enforce the invariance. So what that means is I time differentiate this relationship and then use the governing equations. And that gives me the so-called invariance equation. So I just differentiate both sides, substitute here x dot and y dot where needed, and I have the following expression. Now, this is not very good. This is still a nonlinear equation for h. And in higher dimensions, this would be even more complicated. This would be a partial differential equation. So it doesn't look like much progress. But what saves me is that I know that these SSMs, or this SSM I'm looking for, is actually anchored or fixed to this fixed point. So it goes through the fixed point. And I also know that it is analytic. And this is also something that the theory gives you. So I can look for it in the form of a Taylor series. And when I do that, here I'm just showing the leading order contribution. This is a quadratic manifold that I get to leading order. You can see that in the phase space as well. And then I can also derive the reduced dynamics. And this type of approach already gets you very far. So people have been constructing these invariant manifolds in extremely high dimensional systems, especially my colleagues. They have been dealing with the incredible mechanical systems. And this approach scales very well. However, there is one limitation which I want to show you briefly. And to do that, I introduce this fluid dynamical problem now. So this is two-dimensional Kolmogorov flow. So this is the vorticity equation written on a two-dimensional domain, which is periodic. So it's kind of like a torus, and I'm forcing this with a wave number of 4. And for low values of the Reynolds number, it is known that only this solution is stable. So this is this banded structure. But at a certain Reynolds number, it becomes unstable. And another solution, another stable solution appears, which is this wavy pattern. And I know that there exists a one-dimensional connection between them. So this one-dimensional manifold going from the unstable fixed point to the stable fixed point. And this connection happens to lie along the one-dimensional slow SSM of the stable fixed point. So then it would be really nice if I could, for example, just knowing the stable state, I could expand in a Taylor series this one-dimensional slow SSM, and then it would ideally also go through this unstable fixed point. So that way I could learn something new. I could infer the existence of an unstable point just based on information on the stable point. And this can be done, for example, just to order 3. Here's an approximation for the slow SSM. It is quite good locally, but farther out it deviates. The order 5 approximation is slightly better, but still it doesn't quite go through the fixed point. And here is the issue that is going to pop up. So if I go to very high orders, you see here an order 16 approximation, which locally it's extremely good. And I know that this Taylor series is even convergent on some domains, so this gets better and better. But at some finite distance, it just turns around and does something crazy. So in this case, what happened is the boundary of the domain of convergence was much closer to the stable fixed point than I hoped. This convergent expansion just doesn't cover the unstable fixed point. But I want to emphasize that there is nothing wrong with the underlying SSM. This is just a defect in the Taylor series. And I hope to say something more about this towards the end. There is a way to get around this. But generally, this is a limitation that pushes towards data-driven methods. Because by the attractive properties of these slow SSMs, from data you will always see them. And so therefore you can use the data itself to approximate it and drive your model. And we have developed a pair of software packages in MATLAB and Python that allows you to do that in an automated fashion. These are called SSM Learn. And I would now like to briefly go through how it works, mainly because it helps me fix the jargon, or helps me repeat some of the jargon. So we start with here. Start here. Assume that we know that there's a d-dimensional SSM near an exact coherent state. So this is something that has to be given. But remember that because SSMs grow out of the spectral subspaces, to infer this dimensionality, I just need to do linear analysis. So that's not very hard. But the main difficulty that I run into now is that the phase space in which this manifold lives is usually not accessible. So it's not always realistic to measure all of the degrees of freedom of a system at the same time. But luckily, there are theorems, embedding theorems, that tell you that you can embed this manifold in a different space as long as you have enough observables that you measure along these trajectories. In particular, as long as you have observations more than twice, the number of observations is more than twice the dimension of the SSM, then you can smoothly embed this manifold. So in this observable space, imagine that you have these trajectories coming in and they converge along this SSM to the fixed point. So now I organize them in a data matrix, and the first task is to approximate the coordinate chart. So how do I get reduced coordinates from this manifold? And here we just use a very simple assumption that this manifold is a graph over its spectral subspace. So in fact, this projection to the spectral subspace will be the coordinate chart. And here then I'm constructing the basis for this tangent space. It's enough to do a rough approximation, just maybe using a singular value decomposition, and then projecting with those basis vectors, it gives me a set of reduced coordinates, which I label eta. So then the only question is, how do I go back? So how do I go back from the reduced space to the manifold? and that is the parameterization map. And for the parameterization map, we assume that this can also be written as a polynomial function. This is just a functional approximation task at this point. We could assume also other classical functional approximation methods, but we usually use polynomials, not always, but usually. And then what this problem just means is I have to determine the coefficients of these polynomials, and that is a simple linear regression problem now. So very classical, nothing too fancy with the numerics. But once I have the geometry, now I can go after the reduced dynamics. So I ask how these reduced coordinates, these eta coordinates, evolve among themselves. And as I said, this will typically be a low-dimensional ordinary differential equation for the reduced model. This is the model itself that we derive at the end. And again, I typically assume a polynomial form for this. So determining these coefficients is again just a linear regression problem. I would approximate the observed time derivatives from finite differences or something similar, and then just regress the right-hand side of this polynomial. That gives me the model. Okay, so that roughly covers what I wanted to say about the method and the theory, let's say. So what I want to go to now is a sort of a picture book of applications or a collection of examples that we've applied this methodology to. And to start, I want to show you the so-called inverted flag problem, which is a fluid structure interaction problem. And it's in fact a very nice case study, I think, in model or system identification. So the flag, the inverted flag, is really nothing else, just this elastic sheet that is clamped at one end, and it is subjected to some inflow from the other unclamped end. And then there's this the rest state, or the fixed point of it is when the flag is not moving. That as soon as some flow hits the flag, it becomes unstable, and some more complicated dynamics arises. And so we had Zhenwei Xu, who was a PhD student in our group, and Giovanni Berti, who was a master's student. They worked together with Filippo Coletti, and in Filippo's lab, they built this experiment. You can see a video of it here. The flow is it's in a water tunnel, so the flow is coming from below, and it's hitting the flag, and you can see that this gives rise to some interesting dynamics. In this case, the most prominent feature you notice is the periodic flapping, which some people argue that this could be used for energy harvesting as well. But now, for our purposes, what we want to do is model this dynamics. And an important component to what I said earlier is that we need to somehow anchor this invariant manifold. We have to anchor it to something. And this problem gives us this anchor point very conveniently. So I said that the rest state, when the flag is not moving, it becomes unstable, but it is a fixed point nonetheless of the dynamics. So I can construct its slowest spectral submanifold, slowest SSM. And in this case, it's going to be a so-called mixed mode SSM, because it has repelling and attracting directions, because it's an unstable fixed point. But this is a two-dimensional SSM in this case. And we can construct it by just tracking the endpoint of this flag. So we take measurements of this endpoint as a time series and use then the embedding theorems to construct this SSM. And the reduced dynamics on it is going to be our reduced model. So I'm showing you the phase portrait of this reduced dynamics. This is a two-dimensional dynamical system now that we've inferred from data. You see in the middle, there's the undeflected fixed point. So this is our anchor point. This is a settled type. You can see that some trajectories are leaving, some are approaching it. And this other nice feature is this outer loop in blue, which corresponds to the periodic flapping motion of the flag. And that is represented as a stable limit cycle in this model. So now that I have this model, I could, for example, use it to make predictions on new experiments or experiments that weren't used in the training of this model. And you can see that we are doing a pretty nice job of capturing this transition from low amplitude oscillations to In this case, it jumps pretty quickly to high amplitude oscillations, and the stable periodic flapping sets in. But I think what is more interesting is that if we look at the phase portrait, we see that there are two other fixed points to the left of the undeflected state and to the right of the undeflected state. These would be deflected fixed points. So when the flag sort of buckles to the left or buckles to the right. And this is not something we've enforced in the model. This is something that it came out from the analysis. And physically, of course, it means it makes sense that they are there. So if you think about the mechanics of this problem, it should be, yeah, you should agree that there are these two deflected fixed points in a symmetric way. But still, this is a very quantitative prediction that the model told us. And so then we can test it. And that is exactly what Genway did. So he went back and tried his best to initialize this flag near one of these deflected fixed points. You can see that the deflected fixed points have local unstable spiral type dynamics, as the model would say. So then we can see what happens if I actually run this experiment. So just as the model would predict, we have smaller oscillations in the beginning, and they start to grow until eventually everything is collected by the limit cycle. So in this case, this is a quantitative and qualitatively successful system identification, I would say. Okay, so the next problem I want to show you is turbulent pipe flow. And I think one of the reasons that this pipe flow is so interesting is because of the way it transitions to turbulence. It shows the so-called subcritical route, which means that this laminar profile that is drawn on the diagram never actually becomes unstable, even for infinite Reynolds numbers. But you do see turbulence pop up at some point. So it means that this is an inherently bistable system. So sometimes you see the turbulent state, sometimes you see the laminar state, and it depends on the initial condition that you give in the flow, or that you let the flow evolve from, which attractor, which state you end up in. And this you can also see in the time series of the energy input rate. You can either very quickly laminarize, or you can go to high amplitudes and do these chaotic or turbulent oscillations. And what I want to do with this reduced order modeling task is to capture this bistability. So eventually, at the end of the day, I just want to differentiate between turbulent and non-turbulent initial conditions in some way. And if we want to draw the phase space of this dynamical system in a very sketched way, and this bistability means that there has to be somewhere a boundary between these two attractors. This would be a codimension 1 invariant manifold that separates this phase space. In this case, that is called the edge of chaos. And on one side, you have this turbulent attractor. On the other side, you have the laminar base state. And also, an important feature is that there are also stable states, or not stable, but relatively stable states embedded in the edge of chaos. They are called edge states. And of course, they are globally unstable, but they have just one unstable direction that points away from the edge. So this is what would take you to the turbulent state. And on the other side, this is what would take you to the laminar state. And in this system I'm looking at here, this is a short pipe at a low Reynolds number. This is really just a traveling wave solution, an unstable traveling wave solution, this edge state. And now the strategy is to construct the slow SSM that is attached to this edge state. So in this case, it's going to be two-dimensional. It will have two directions, one unstable, so it will contain for sure the unstable manifold of this edge state, but it will also contain the slowest direction inside the edge. So you can sort of imagine it like this, that we're cutting across with the slow SSM along the edge of chaos. It will for sure intersect transversely. And therefore, if I reduce the system to this slow SSM, in the reduced order model, I will have to have some footprint or some imprint of the edge of chaos inside this reduced model. So that will allow me to differentiate between turbulent and non-turbulent initial conditions. And I just want to note that for now, I ignore the turbulent state. So once they get far enough, I don't want to bother with it too much. I'm fine with just differentiating between the two types of initial conditions. So now we again use data, but this is a DNS now. So this is not an experiment, unfortunately. But we use this DNS solver open pipe flow to initialize trajectories that are close to this edge state, but they are on both sides of this edge of chaos. So they can either go to turbulence or they can go to the laminar flow. And using that data, I now fit this SSM, this two-dimensional slow SSM. In this diagram or this visualization, I'm using the energy dissipation rate D and energy input rate I as reduced coordinates. So they are in fact physical coordinates, and the Z direction is just the kinetic energy for visualization. But here I'm actually reconstructing all of the degrees of freedom of the system. So I could pick any other degree of freedom. And then in this space, you see this SSM, the slow SSM is this green surface. And the edge of chaos would be cutting across it somehow in where I drew this blue surface. Now, unfortunately, the edge of chaos is very high dimensional. To be honest, I have no idea how it looks like. I wouldn't know how to draw this. So this is just a cartoon. But what is not a cartoon that is for sure exists here is this orange line. So that is where the edge of chaos and my slow SSM intersect. So that is already a prediction from this reduced model, and is probably best understood if I look at the phase diagram or a phase portrait of this dynamical system. So again, this is a two-dimensional vector field. Here is our anchor point. This is the edge state, and down here is the laminar state. Turbulence would be somewhere up here, but I don't care about that. I cut everything that leaves the box. And this intersection point, this footprint of the edge of chaos, is really nothing else, just a stable manifold of this saddle type fixed point that I have here. And in this two-dimensional vector field, it's actually super easy to find. So I can just integrate backwards along the stable eigenvector, and that would trace out this curve. And this is something, again, that we can test. So what we've done is prepare a grid of initial conditions that are intersecting this edge footprint. So they are near this edge state, but they live in the full phase space of the Navier-Stokes. And then I simply let them evolve under the DNS, so under the full model. And what we see is that this grid is cut very nicely in half, precisely where our prediction for this edge intersection would be. So anything above transitions to turbulence, anything below laminarizes quickly. So what this tells me is that this one-dimensional object is a real structure that has real dynamical significance for the dynamics of the Navier-Stokes. But of course, you could say that this is just a glorified binary classifier, right? Because I'm just differentiating between these two types of behaviors. And that is true, except that here the binary classification is done by the geometry of this invariant manifold. I'm just trying to find a clever way, or well, not even clever, just a way to get to this geometry, to use that. But still, it would be nice to model some more complex behavior as well. And to do that, we actually have to turn to a different flow, which is simpler in some sense, but still similar to pipe flow. And this is going to be plain Couette flow. So this is a flow between two planes, two walls that are moving in the opposite direction. So they induce a shear. And this flow is also subcritical. So it's transitions to turbulence in a subcritical way, because this constant shear solution, this linear profile, is again always stable, no matter how large the Reynolds number is. But we can see complexity appear here at a much lower Reynolds number than previously, than we've worked with previously. So if we follow this bifurcation diagram constructed very nicely by Krylos and Eckhart, we see that At a Reynolds number even below 200, there is an extended chaotic attractor that is born as a sequence of bifurcations. And the other side of this chaotic attractor, or there's also an edge state or an edge of chaos that mediates the transitions between the laminar attractor and the chaotic attractor. That is this lower branch fixed point solution. I'll compute it first by Nagata. But I would like to emphasize that this is not yet turbulence. This will be a chaotic flow. So this is not, this is temporally complex, but not yet spatial temporally. So this would be a baby step towards turbulence. But essentially what we wanted to see is, can we apply the same methodology? So, right, we have an edge state, we have this unstable fixed point here, we have a turbulent or a chaotic attractor on one side, we have a laminar attractor on the other side. And what if we constructed the slowest SSM of the system, the slowest SSM anchored to the edge state? Can that capture chaos potentially? And the spectrum of the linear dynamics near the edge state now is of saddle spiral type. So there is a one-dimensional unstable direction and a stable direction, a stable spiral, which is now two-dimensional. So that means altogether my manifold is going to be three-dimensional. So going from 2 to 3 now, but if I construct that with given some simulation data also from a DNS solver, then I can derive a model that does very well on short-term predictions, even in the chaotic state. Of course, in the chaotic state, we know that long-term predictions are impossible because of the sensitive dependence on initial conditions. But it can nicely differentiate between laminarizing and chaotic trajectories. And also it captures the long-term statistics of the chaotic attractor. So this is the parallel spectral density computed on the chaotic attractor. You can see that we're doing an okay job. And here's a visualization of what happens in the reduced phase space. So here on the left, this is the attractor in the reduced space. And here, this is what would happen in the real space. So when I use the parametrization to go back to the phase space and translate that to the physical space, the channel. So when I let this simulation evolve, so you see that we very quickly jump to the attractor and then complete these twists and turns in whatever way along it. You can see that we have this chaotic wiggling of the vortices of the Couette flow. Yeah, and maybe I'm a bit behind on time, so I thought I would skip ahead. I skip one example and skip to my last example, which unfortunately this is not a fluid dynamical problem, but a solid mechanical problem. I hope you will forgive this, but I was very excited about these results, so I couldn't resist keeping them in the presentation. And this will be a beam model, so a finite element model of a beam that is clamped on both ends. And here we're going to use the equations. So this will be a very similar example to the Kolmogorov flow I showed in the beginning. So no simulation data required here. And imagine we have this finite element model of the beam. It's clamped on both sides, and I'm starting to push on it from one side in a horizontal way. Then we know that if the force is big enough, then this beam will buckle. So this straight configuration where there's no deformation or no deflection, it becomes unstable, and then the beam snaps either up or it snaps down. And then these two new fixed points, which are now stable, they are born in a bifurcation. So much like with Kolmogorov flow, I thought a good question to ask would be, okay, well, this is a very simple state, the undeflected state. What if I construct a slow SSM that is attached to the simple state? Can that give me information about the new states that are born, about these buckled states? And unfortunately, the answer is no, at least if you go by the Taylor series assumption or Taylor series method. If you construct this SSM as a Taylor series approximation, you can see that locally near the buckled state, it's doing a very good job. But just before it could reach the two new steady states, it just sort of falls off a cliff. and it stops converging and diverges. So this would not be a very good model, again, for this dynamical system. At least locally it's good, but not globally. And we came, long story short, we came up with a way to get around this limitation. So we realized that if only we could convert the Taylor series expansion that we've invested a lot of time into to some other representation that may have different and better convergence properties. In particular, if we convert it to rational functions, or a rational function approximation, or a Pade approximant, then it is known that they have a potential to converge on much larger domains than the Taylor series. And a very important point is that, so here's the rational function expression. This is just a ratio of two polynomials. And I want to emphasize that I don't need to do any new computations here. So once the Taylor series coefficients are determined, I can then translate them directly to the rational function coefficients. So no new computation required. But still, look, they converge in a much larger domain. So they have this nice big surface that we can trace out, which now supports the two new fixed points. These are spiral type stable fixed points corresponding to the buccal states. So you could say that we've globalized this SSM, we've enlarged this SSM, and that's why we call it GSSM. And that is very lucky. So now we have some dynamical information on how this buckling takes place, for example. But I would say that the reason this is even more important is that now I have a model of the system that I can trust. So I can try pushing it to its limits, maybe playing with it a little bit and see if that reproduces some actual phenomena. So I can try to learn new things, right? For example, I could ask what happens if I add periodic forcing. So I have this buckled fixed point, and I start pushing on the middle node with the periodic force, just in a vertical direction. It would be reasonable to ask what is the response of the system to this harmonic perturbation. And the good news is that because we have invested a lot of time in figuring out the analytic properties of these SSMs, we know that this is smooth in perturbations. So just because I'm perturbing it with or I'm modifying the system to have a periodic forcing, the SSM is not going to disappear. But I can just write in a systematic way of accounting for this periodic perturbation. And it turns out that to leading order, that's just the most important contribution, is actually just comes from the reduced dynamics. So I don't need to modify the parametrization to leading order, but I can add the forcing in a projected fashion. So I project the forcing to the tangent space of this SSM, I just add it to the autonomous vector field, and that gives me a forced two-dimensional system here. And then I can explore that. I can ask what is happening in the real system. And surprisingly, or maybe not surprisingly, depending on how much you've worked with these kinds of systems, this will actually give rise to chaotic response very often, depending on the amplitude and the frequency of the perturbation, but it can respond chaotically. And this is what you see in the full phase space. So then this chaotic response, this is a full-blown homoclinic tangle that is born on this attractor, or the attractor is born on the invariant manifold. And then I can use the two-dimensional dynamics to simulate what is happening in the real space. You can see a video comparison of this. So I would
Yeah, I guess we lost Balint. That's where for a while.
Yeah. Hope he knows.
Hello, I disconnected or
Yes, we lost you.
I'm sorry.
No worries.
I think I was on the last slide anyway, so
Okay.
or did you hear it up to the last slide or?
I think you were talking on the slide on the chaotic buckle beam. Maybe just lost you for around 1.5 and 2 minutes.
I think we lost him again.
I'm sorry.
No worries, it happens.
So you were saying I stopped where?
On the slide about the chaotic buckle beam.
Okay, yeah. Maybe just if you allow me to just wrap up very quickly.
Yeah.
Yeah. So was it here already?
Yes.
Okay,
Yeah.
good. Okay, then I was at the end. So I was just saying that we could predict the chaotic response of this beam, and that is facilitated by this analytic knowledge we have of these manifolds. We know that they are smooth in the parameters of the system. And in one sentence, just to recap, I hope to have convinced you that these SSMs they provide a strong foundation for invariant manifold-based model reduction, because what they allow you to do is to anchor these invariant manifolds to something other than just viewing them as flying carpets in the phase space. And because of the very strong mathematical results, we know that they allow us to learn new things about the systems and extrapolate to new dynamical regimes. So very sorry for the disconnect, and thank you very much for your attention.
Okay. Yeah. Thanks for the wonderful talk, Balint. So now we have the Q&A section. If the audience have a question, please feel free to unmute yourself or post your question to the chat room. So while we wait for the audience to get their thoughts, I'll jump in to ask some simple questions to kick things off. So please bear with me if it seems straightforward. So I think my first question is how. So I think your example on the fluid structure interaction on the pipe and the pipe flow problem, both of those you use a two-dimensional latent coordinate system for the
Right.
SSM. Is that right?
Right. Yeah.
So may I ask how? Is there a rationale how you choose like a two-dimensional SSM, or how do you determine the dimension there?
Yeah, it's a very good question, and that's so usually locating this exact coherent state that we anchor to and determining the dimension. That's the main issues or main difficulty, that I should say. So here for example with the pipe flow, here I know roughly the spectrum of this edge state, so I can count, or I can look at the leading eigenvalues, the slowest eigenvalues. What I see is that there is one real eigenvalue that is positive, so that would be unstable, and the next slowest one is real but stable, so real and negative. So that means if I want to construct something that is larger than the unstable manifold but still the slowest manifold, then I need to pick a two-dimensional spectral subspace that spans this. And very similarly with this one. Here we didn't know the linear part of the operator because we don't know the operator, but just by time series analysis, you can find out that it also has a real and or two real eigenvalues, one on each side of zero. So therefore, that is what you pick.
See.
Yep.
Okay. Yeah, Philip asked a question. So let me just read this out. So he asked, does this method help us understand or model the atmosphere?
Yeah, so that's a good question. I'm wondering the same thing. So I hope to work on this a little bit later. Um, what I will say is that I put Ed Lorenz here as a reference, and the reason is he started talking about these slow manifolds, these atmospheric slow manifolds, very early on, and in some sense his idea was more in terms of frequencies. So um, so enslaving or finding a relationship between low frequency and high frequency motions, and that turned out to be not a very useful concept. But if you turn this around and look at the relationship between decay rates, such as SSMs, such like you do with SSMs, then this could potentially be a way to go towards these slow atmospheric manifolds as well. I hope. Yeah.
Okay. Maybe I can ask one more question. So actually that's related to on your last slide, you talk about the generalizability. So I'm thinking about like, okay, your method can, after you create this model, you can use it to predict the behavior in the same system. But how about if, say, there is a shift in the parameters, like if you have a different Reynolds number? So I can you explain to us what are the difficulties or faults that you may want to do to generalize your models? Because I know like the ECS and the Jacobian could change.
Yeah, that's also a good point. In general, as long as you know that the dimension of the slowest manifold or the slowest spectral submanifold doesn't change, then this will also be smoothed in parameters such as the Reynolds number. So I don't know if I have yeah, here I have a slide. So in Pipeflow, we have done this in a Reynolds number dependent way. It's not very interesting because no bifurcations happen in this range. But if this assumption is true that your leading or slowest spectral submanifold is always two-dimensional, then you can just do this in a Reynolds number dependent way.
See.
But yeah, with bifurcations, you kind of have to be careful because then some of these assumptions that go into the well, at bifurcations, you know that these turn into center manifolds, so that's a different type of manifold, and we're currently thinking of how to stitch that all together. It's not very simple, but I think it is doable.
See. There's a new question from Rochelle asking in terms of computational efficiency, so going to a nonlinear SSM means we may suffer from the increased computations. Compared to a linear model, what could be the rollout more efficiently? Can you speak of this, please?
Yeah, it's so in a data-driven setting, I think these types of equations are relevant to show here. So the good thing is that we don't need to go to very high dimensions. So evaluating these polynomials, this is a polynomial of maybe 2 or 3 variables. Evaluating or fitting it is basically instantaneous. It's not very computationally heavy. And same with the reduced dynamics. Now, if you needed a really high dimensional SSM, like for some reason you had maybe internal resonances and you needed to fit a 10 or 20 dimensional SSM, then I wouldn't know what to do immediately. So for example, probably you need to turn to different function approximation methods that are more efficient, would be my guess.